Hi all, let me first introduce myself. I am Anu Paes, working as Assistant Professor in CSC Department in J. Bharat Engineering College. Today we are going to talk about LR Parsing. So the most prevalent type of bottom-up parser today is based on a concept called LRK parsing. So what is this LRK parsing? So here the letter L, it refers to left to right scanning of input. R denotes constructing a rightmost derivation, and K, it represents the number of input symbols of look ahead. That means when we are passing, how many strings or input symbols we will be considering while we are doing the passing operation. So when K is omitted, it is assumed to be 1. These LR parsers are table driven, like non-recursive predictive parser. So in order to understand more about this LR parsing, we have to first know what is an LR grammar. So I hope you remember what is a grammar, what is a context free grammar, etc. So this is a new concept. So how it differs from others is because of two main restrictions. So first is that no production has an empty RHS. So what does it mean? There should not be any epsilon productions. Number 2 is no production has two adjacent non-terminals in its RHS. So if there is one non-terminal symbol in RHS, there should be an adjacent terminal symbol or no symbols, but there should not be any two adjacent non-terminal symbols. So if you see that example, E giving E plus E or E into E or ID. So here there are no adjacent non-terminal symbols or there are no epsilon productions. So this is an example for LR grammar. So why this LR grammar is important? Because a grammar for which we can construct a parsing table is said to be an LR grammar. So for an LR grammar, we can construct a parsing table. So next we are going to see why we are using LR parsers. Okay, so the first point is it can be constructed to recognize virtually all programming constructs for which a CFG can be written. So for every programming construct for which a CFG can be written, we can construct an LR parser corresponding for that. Second one is that it is a most general non-backtracking shift reduce parsing method. So we have seen what is non-backtracking and how we are doing shift reduce parsing also. So LR parsing method is most general non-backtracking shift reduce parsing method, that is non. And third point is that it can detect a syntactic error very quickly. Now last point is that it's a class of grammars that can be parsed using LR method is a proper superset of class of grammars that can be parsed with predictive or LL methods. So if we can do parsing for LR method, we can do parsing for LL method and predictive operator predictive parsing method. So next we are going to see important concepts we need to create this LR parsing table. So first is item. So let us see what is an item. Before that, an LR parser makes shift reduce decisions by maintaining states. Okay, we have seen NFA, DFA, etc., and we have seen what is state. So similarly here also we will be making use of states. So state represent a set of items. So what is an item? So LR 0 item of a grammar G is a production of G with a dot at some position of the body. See, suppose we have a production and here there will be a dot and that dot can be at any position of that production. So for example, let us consider this production A giving XYZ. Okay, so it yields the 4 items. Which are the 4 items? The dot can be at the first position, that is A giving dot XYZ. Second is the dot can be after the first terminal or non-terminal symbol, so A giving X dot YZ. Now third is after two terminal or non-terminal symbols, so in this example after XY, and last one is at the end of that, so A after X, Y and C. So these are called items. Okay, and what is the relevance of that dot? Okay, so dot, it represents how much of a production we have seen at a given point in the parsing process. So if it is A giving dot XYZ, it means we have not passed through any of that XYZ symbols. If it is A giving X dot YZ, then it means we have passed X and YZ is remaining. So that is the relevance of item. So next is LR0 automation. So we have seen finite automation, so we can look at what is LR0 automation. So one collection of set of LR0 item is called canonical LR0 collection, and it provides a basis for constructing a DFA that is used to make parsing decisions. Okay, so a set of LR0 items is called LR0 collection, and it provides a basis for constructing DFA. Okay, when we go through an example you will understand this, so for now you just keep it in mind. So such an automation is called LR0 automation. So what is an automation? We have seen while we studied NFA, DFA, etc. There will be states and there will be transitions also. Similarly, we will be doing in this LR parsing also. So we will see it later. Each state of this LR0 automation represents a set of items in canonical LR0 collection. Okay, so just understand that a set of canonical LR0 collections makes a set of LR0 items is called a set of LR0 canonical collection. Okay, so next is augmented grammar. So first we have to create an augmented grammar for creating an LR parser. So what is an augmented grammar? We will be adding one extra production to the regular grammar. For example, E giving E plus T or T, T giving T star F or F giving E or ID. So here the start symbol is capital E. So we will add a new production, that is E dash giving E. So if we are adding this additional production to the beginning of the grammar, this grammar becomes an augmented grammar. So that is stated above. If G is a grammar with start symbol S, then G dash, the augmented grammar is G with a new start symbol S dash and production S dash giving S. So keep in mind what an augmented grammar is. So next is closure. Now this closure is also important. To understand the concept of closure is very important. So if I is a set of items for a grammar G, then closure of I is a set of items constructed from I by the two rules. Okay, to compute closure of I. What is I? I is a set of items. And what is an item? If we have a set of production with a dot operator in any particular position, then it is an item. So set of items is I. Then how we can compute the closure? Add every item in I to closure of I. Okay, so if we want to compute closure of I, then we have to add every item of I in closure of I. That is the first step. Second is, if A giving alpha dot B beta is a production in closure of I. Okay, note that the dot operator is after alpha and before the symbol capital B. Then what we have to do? Then we have to check whether there is a production B giving gamma. Okay, so that is if there is a dot operator in our closure. Okay, then we have to check whether there is a production to the symbol to the that is to the right of the dot operator. Then add the item B dot giving dot gamma to closure of I if it is not already there. Okay, and we have to apply this rule continuously until there are no more new items. So let us see an example. Okay, before going to an example, let us see what is a kernel item and a non-kernel item. So kernel item, it includes the initial item, that is s dash giving dot s, and all items whose dots are not at the left end. Okay, so s dash giving dot s is included as kernel item, and all other items whose dot are not at the left end are kernel items. Now we'll see what is a non-kernel item. All items with a dot at the left end except for s dash giving dot s is the non-kernel items. So that is the definition of kernel and non-kernel items. Now we will see an example for computing the closure. So our grammar is s giving a and a giving a small a, capital A, or small p. So first step is we have to create the augmented grammar so that we can do the parsing operation. So how will we do that augmentation? We will add the production s dash giving s. So we have this augmented grammar here, s dash giving s, then remaining production is same as that of the question. Now how we will compute the closure of first statement s dash giving dot s. Okay, so for that we will place dot operator to the first, so s dash giving dot s. Okay, similarly next production is s giving dot a. Okay, and similarly a giving dot a or b. So in the slide there is a small mistake over there, so s giving dot a or dot b. Okay, so we have to apply closure to every operation, after doing a Goto operation. So next we are going to discuss about what is a Goto operation. So in this Goto, it accepts two symbols. Okay, so first symbol is capital I, that is a set of items, and second symbol is grammar symbol. It can be either a terminal symbol or a non-terminal symbol. So it takes two inputs. First input is the set of items and second input is a grammar symbol. And please note that capital X can be terminal as well as non-terminal. So how we can define Goto? So define to be closure of set of all items A giving alpha x dot beta such that A giving alpha dot x beta is in I. Okay, so we will see this example, and looking at that you will get a better idea of closure as well as Goto. So see, our grammar was s dash giving s giving a and a giving a or b. So I have made a closure of first set. Okay, that is s dash giving dot s giving dot a and a giving dot a or dot b. That is the first set of closure. Okay, so that set of items we have. Now we are going to compute the Goto. So for computing Goto, what you have to do is you have to take each and every productions and you have to shift that dot operator one to the right. So if you take that first production s dash giving dot s, if you shift the dot operator once to the right, what you get? You will get s dash giving s dot. Okay, so we are going to make it another set. So is it possible to create any other closure or include any other closure within that? No, because after dot operator there is no symbol, so we won't get any more closure in that. Okay, so I hope that you have understood how we got the closure for this s dash giving dot s. Why we included the first production as that s dash giving dot s first, then after dot operator we had s, so we had to include that production as giving dot aa. We had capital A after the dot operator in the second production, so we included that production A giving dot aa or dot b. No more productions are available, so that formed a list of closures. Now s dash giving s dot, further closure is not possible. So how did we get that transition? By s. Okay, so what it means is, when the state changes from first state to second state, we will get s as the output, or we will reduce by s. That is the meaning. So that is go to operation. Now let us see next thing, that is we will see for capital A. Okay, so first we move this dot operator one to the right for the first production. Now we will move the dot operator to the right for the second production. Okay, so s giving capital A dot A. Okay, and that closure, it includes the next production also. Why? Because after dot operator we have capital A, so we have to include capital A giving dot aa slash dot b. Further we cannot add any items to that closure. Okay, so how did we get that set? By moving dot operator one to the right, and when moving we across the non-terminal capital A, so we wrote capital A. So that is the go to operation. Now we will do the same operation for the third production. Okay, so when we move the dot operator one to the right, we will get A giving small a dot capital A, and A giving what then how we got this second production? Because after dot operator we have a capital A, so we should include the closure, include in that closure that production also. Okay, so that two together form the closure. Now for that we move the dot operator one to the right of small a, that is why we have marked small a in that arrow. Now similarly we have to move that dot operator one to the right of small b, so we got a giving b dot, and the b marked with small b. Okay, so similarly we have to do this for the new set of productions, that were new set of items that we got. Okay, so the first one is s dash giving s dot. We cannot find any more closure for that, so we will be stopping with that. Now we'll take the next set or state. So s giving a dot a and a giving dot a bar dot b. So here one shift is possible with capital A, so we have got s giving a dot. Now no more closure will be included in that set. Now when we say take the second production, when we move small a to one position right, and see, we will be getting the same production as we have written down, so I have marked it towards that set. And similarly for the next set also, when we move similarly for that one, when we take in the case of a giving small b, the dot operator, a giving b dot we will get. So that is why there is an arrow moving from that state to the state. Okay, so similarly we can compute Goto for every operation. So we will be stopping this procedure till we get dot operator at the end. So s dash giving s dot, s giving a dot, and a giving a dot, and a giving b dot. So hope you have understood how to compute closure as well as Goto. So in today's class, we learned about LR parsing, LR grammar, pros and cons of LR grammar, and how to compute closure and how to compute Goto. So next lecture will contain how we'll be doing this parsing, that is parsing algorithm, and how we'll be constructing this LR parsing table. So